Now with conditional probability, multiplication theorem and total probability theorem, we can come to one of the most important theorems in probability, and that is Bayes theorem. And Bayes theorem setup will be same as that in the case of total probability. So there will be this event whose probability is going to depend on outcome of the previous mutually exclusive and exhaustive events. So again, let A1, A2 and AN be mutually exclusive and exhaustive events, and then we have this event A which can happen with either A1 or A2 or AN. Then from total probability we know that this probability of occurrence of A will be given by this summation I varies from 1 to n probability of AI into probability of A upon AI. So in this case we have n events A1, A2, AK and AN which are mutually exclusive and exhaustive, and then we have this event A which can happen with either A1 or A2 or AK or AN. We find these probabilities, probability of A1, probability of A2, probability of AK, probability of AN, and then their corresponding conditional probabilities A upon A1, probability of A upon A2, probability of A upon AK, and probability of A upon AN. And if we multiply them and add them, we'll get total probability, which we have already studied. So in total probability, we find the probability of occurrence of this event A. Now, if it is a Bayes theorem question, it will say that this A has already occurred. So in the Bayes theorem, it will say A has already occurred. So we know that. So now we know that this event A, it has already occurred. Generally in the question of Bayes theorem, there is a keyword called is found to be. So for most of the Bayes theorem question, you will find this keyword that something is found to be. So that means this A has already occurred. So now in Bayes theorem, it will ask if this second event has already happened, then find the probability that it has happened through any one particular previous event, say this AK. So in this case, we have to find this probability that if A has already occurred, then this previous event was this event AK. So in Bayes theorem, all we simply need to do is we'll take this case, which are favorable case in the numerator. So it will be this probability of AK into probability of A by AK and total probability in the denominator, that is total probability of occurrence of this event A. So it will be this probability of AI, probability of A upon AI, where I varies from 1 to n, and this is our Bayes theorem. So in Bayes theorem, all we need to do is we need to list the problem as we have done in case of total probability. We have to work out these individual probabilities and their conditional probabilities. Now we have to find probability of any one particular event AK. We'll take this case in the numerator and we'll take sum of products of all the cases in the denominator, and this is how we solve Bayes theorem questions. Now if we come back to our box example, this question was total probability question. Now if it is Bayes theorem question, it will say a ball is drawn and is found to be red. Find the probability that it has come from any one box, say box 1. Our setup was box 1, box 2, probability of choosing box 1, 1 by 2, probability of choosing box 2, 1 by 2. This is red, probability of red from box 1, it is 1 by 2, and probability of red from second box, it is 1 by 4. Now we have to find the probability that if the ball is red, it has come from box 1. So we have to find, we already know it is red ball. It has come from box 1. So we'll take this case of first box in the numerator. So it will be this 1 by 2 into 1 by 2 in the numerator upon this total probability in the denominator. So it is 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 4. It will be simply 2 by 3. So on the same total probability setup, we have defined a Bayes theorem question. And if we come to our second example, in total probability, we have worked out the probability that the product is defective. Now, if it is Bayes theorem question, it will say a product is drawn and is found to be defective. Then find the probability it has come from machine B. So now we need to find this probability that it has come from machine B if we know product is defective. Now we'll take this case of B in the numerator. So it will be this 30 by 100 into 2 by 100 upon this total probability 60 by 100 into this plus 30 by 100 into 2 by 100 plus 10 by 100 into 3 by 100. This we have already worked out. So it will be this 150 by 10,000 will cancel. Now this probability is 2 by 5. So probability that this defective product it has come from machine B is 2 by 5. Now in total probability and Bayes theorem, there can be questions where we have this event A whose probability is going to depend on outcome of some mutually exclusive and exhaustive events BI, and whose outcome in turn they depend on outcomes of some events C's, and which itself depends on some D's, and so on and so forth. So we may have nested conditions in total probability. In such cases, the best method to go forward is using tree diagram. Now say for example, we have a bag, and in this bag we have n fair coins and we have one two-headed coin. Now it says a coin is tossed. Now, if this coin result in head, this same coin is tossed again, and if this coin it results in tail, then a coin is chosen from remaining coins and it is tossed. First we'll deal with total probability question, and we'll say we have to find the probability that we get two heads. So we toss a coin, and if it shows head, we'll toss the same coin again, and if it is tail, we'll choose another coin and then we'll toss it, and we have to find the probability that we get two heads. Now the situation looks a little complicated, but what we'll do is we'll draw a tree diagram. So we have this coin. Now this coin, it can be a fair coin or it can be a two-headed coin. Now what is the probability of choosing fair coin? Now out of n plus 1 coins in the bag, we have n fair coins. So the probability of choosing a fair coin is n upon n plus 1. Now what is the probability of choosing a two-headed coin? So if it is two-headed coin, then probability of choosing two-headed coin is 1 upon n plus 1. Now if we toss this fair coin, we'll either get a head or a tail. Now on a fair coin, probability of throwing a head, it is 1 by 2, and probability of getting a tail is 1 by 2. Now on two-headed coin, we are certain to get a head only. So in this case, this probability is 1. Now the question says, if it is head, then the same coin, it is tossed again. So if it is head, we'll throw this fair coin again, which can again result in head tail. So again, probability of choosing head is 1 by 2 and probability of getting a tail is 1 by 2. And if it is tail, then we choose another coin from remaining n coins. Now, if we choose another coin, then that coin, it can be a fair coin or it can be a two-headed coin. Now, probability of it being a fair coin. So now we have n minus 1 fair coins and n total coins. So this probability of choosing a fair coin is n minus 1 by n, and probability of choosing a two-headed coin is 1 by n. And in this case, it is only head. Now, if it is head, we'll toss this coin again, and again it will result in head. This probability is 1. Now, if it is fair coin, if we toss it, we'll get either head or tail. So it will be this 1 by 2, 1 by 2. And if it is a two-headed coin, we are sure to get this head, and this probability is 1. Now we have to find the probability that we get two heads. Now we get two heads. In this case, so this is n plus 1 into 1 by 2 into 1 by 2 plus this case, which is 1 upon n plus 1 into 1 into 1. So this is n plus 4 upon 4 into n plus 1. And if it is Bayes theorem question, it will say if two tosses resulted in two heads, find the probability that first coin tossed was a two-headed coin. So that means we are talking about this case. So if it is Bayes theorem, we'll take this case in the numerator and this total probability in the denominator. So in this case, we have to find the probability that it was two-headed coin provided it resulted in two heads. So we'll take this case in the numerator. So it will be 1 upon n plus 1 into 1 into 1 upon this total probability, this into this into this plus this into this into this. So we have already worked it out. So this is n plus 4 plus 4 into n plus 1. Now this n plus 1 will cancel. So it will be 4 upon n plus 4. So in these cases, it is better and recommended that for such cases, you use tree diagrams. Now here the question is, urn A contains 6 red and 4 black. So we have this urn A which contains 6 red and 4 black balls. And then we have this urn B which has 4 red and 6 black balls. Now one ball is drawn at random from A and placed in B. So we have taken one ball and we have placed it in B. Then one ball is drawn from urn B and placed in A. So we have taken one ball from B and we have put it back in urn A. If the one ball is now drawn from A, we need to find the probability that this ball is red. Now we'll start with this urn A, and in urn A we have 6 red and 4 black balls. Now one ball is transferred to urn B. Now this one transferred ball, it could be either red or black. Now the probability that it is red, it is given by 6 by 10, and it is black with the probability 4 by 10. Now if it is red, in urn B we have 5 red and 6 black. And if it is black, we now have 4 red and 7 black in B. So this is the position of B after the first transfer. Now again from B, we have transferred one ball back to A. Now if the ball transferred is red or black, and again here it could be either red or black. Now it'll be red with the probability 5 by 11 and black with the probability 6 by 11, and here it is red with the probability 4 by 11 and black with the probability 7 by 11. Now if it is red, we have 6 red and 4 black in A. If it is black and the first ball gone was red, so now we have 5 red and 5 black. Now previously, if black goes out from A and red comes in, it'll be 7 red and 3 black, and here it'll be 6 red and 4 black. So this is the configuration for A. Now from this, we need to find the probability that the ball drawn is red. Now here ball drawn is red with the probability 6 by 10. Here it is 5 by 10. Here it is 7 by 10. And here it is 6 by 10. So this required probability is sum of product of all these cases, which is 6 by 10 into 5 by 11 into 6 by 10 plus 6 by 10 into 6 by 11 into 5 by 10 plus 4 by 10 into 4 by 11 into 7 by 10 plus 4 by 10 into 7 by 11 into 6 by 10. And the denominator will have 1100, and here will be 6 into 6 into 5 2 times. So there will be 36 into 10, which is 360. And here we have 74, 28, 28 into 10, 280. Now we'll cancel this 0. So this is 36 plus 28, 64 divided by 110, which is 32 upon 55. And that's your option 1. Now the question is, a bag contains some white and some black balls, all combinations of balls being equally likely. The total number of balls in the bag is 10. If 3 balls are drawn at random without replacement and all of them are found to be black, find the probability that bag contains 1 white and 9 black balls. Now since we have already drawn 3 black, it means at least it should have 3 black balls. So let us say this bag has R black and 10 minus R white balls, where R varies from 3 to 10. Now each of these cases, they are equally likely. So we have total 8 cases. So probability that R is 3, R is 4 up to R is 10, it is 1 by 8 in each case. Now when we have R black and 10 minus R white, then the probability of choosing 3 black will be given by RC3 upon 10C3. So this probability that we'll drop 3 black balls will be this summation 1 by 8. R varies from 3 to 10 RC3 upon 10C3. Now it says, if it has already occurred, if you already know that 3 balls are black, find the probability that it contains 1 white and 9 black balls. So we have to find this probability that value of R is 9. So this probability that R is 9, given that the 3 balls are black, it is given by this case. This case is 1 by 8 into 9C3 upon 10C3 divided by 1 by 8 into this summation RC3 upon 10C3. Now 1 by 8 will cancel, 10C3 will also cancel. So we'll get this as 9C3, and here it will be 3C3 plus 4C3 up to 10C3. Now we can write this 3C3 as 4C4. Now n same R differs by 1, so it will be 5C4. Next one will be 6C4. So finally it will be this 11C4. So this required probability will be 9C3 upon 11C4. Now this is factorial 9, factorial 3, factorial 6, and here will be this factorial 11, factorial 4 and factorial 7. Now here will be this 4 into 7, and this one is going to be 11 into 10. So this probability will be 14 upon 55, and that's your option 1. Now here the question is, a bag A contains 4 red and 5 black balls. Another bag B contains 6 red and 3 black balls. And a third bag C contains 3 red and 6 black balls. A bag is selected and a ball is drawn at random from the bags. If A, B, C denote the events of selecting bags A, B and C respectively, and E and F denote the events of getting red and black ball respectively, then find the following probabilities. Now we have 3 bags, A, B and C. Now A has 4 red and 5 black. B has 6 red and 3 black. And C has 3 red and 6 black balls. Now probability of choosing any one bag is 1 by 3, 1 by 3 and 1 by 3. Now probability of choosing this event E, which is getting a red ball. So probability of E by A is 4 by 9. E by B is 6 by 9. And E by C is 3 by 9. Now the first question is, we need to find this probability, which is probability of E upon A union B. Now probability of E upon A union B is probability of getting a red ball if it is either A or B. Now we can write this as probability of A union B intersection E upon probability of A union B. Now choosing A and B, it is mutually exclusive event. So we can write this as probability of A intersection E plus probability of B intersection E upon probability of A plus probability of B. Now probability of A intersection E is 1 by 3 into 4 by 9, and B intersection E is 6 by 9, and PA plus PB is simply 2 by 3. Now 1 by 3 will cancel. Now this value is 10 by 9 divided by 2. So it will be this 5 by 9, and that's your option C. Now the second one is, we need to find, if it is a red ball, we need to find the probability that it has come from this bag A. Now this is nothing but Bayes theorem. So we'll take this case of A in the numerator. So it will be 1 by 3 into 4 by 9 upon, now this is 1 by 3, and here it is 4 by 9 plus 6 by 9 plus 3 by 9. Now 1 by 3 will cancel. This 9 will also cancel. Now this is 4 by 13, and which is your option A. And finally it is, find the probability of getting a black ball. Now probability of getting a black ball is this 1 by 3. Now black from this is 5 by 9. From this one it is 3 by 9, and here it is 6 by 9. Now this is 14 by 27, and that's your option D. Now the question is, we have two urns, urn 1 and urn 2. Urn 1 contains 4 white and 5 black balls. Urn 2 contains 3 white and 6 black balls. Now it says one urn is chosen at random and a ball is drawn. Its color is noted and replaced back to the urn. Again, a ball is drawn from the same urn, color is noted and replaced. The process is repeated 4 times. And as a result, 1 ball of white color and 3 of black color are noted. Find the probability that chosen urn was urn 1. Now let this event be A. Now probability of choosing any urn, suppose probability of choosing urn 1 will be equal to probability of choosing urn 2 because they are equally likely, and there will be 1 by 2. Now if we choose urn 1, then probability of getting a white ball and 3 black balls will be probability of A by U1, and it will be 4C1 into, now probability of white is 4 by 9, probability of black is 5 by 9. So there will be 4C1 4 by 9 into 5 by 9 cube. Now in the same way, for the second urn, again we have 1 white, so there will be 4C1. Now here probability of white is 3 by 9 and probability of black is 6 by 9. So there will be 6 by 9 whole cube. Now it's a Bayes theorem question. So it says, if this event has already occurred, we need to find the probability that chosen urn was urn 1. So we need to find probability of having urn 1 if A has already occurred. So we'll take this case in the numerator. So it will be this 1 by 2 and 4C1. This is 4 by 9 into 5 by 9 cube upon 1 by 2 into 4C1, 4 by 9, 5 by 9 cube plus 1 by 2 into 4C1, 3 by 9 into 6 by 9 whole cube. Now 1 by 2 4C1 will cancel, and this 9 to the power 4 will also cancel. So this result will be this 4 into 5 cube plus 4 into 5 cube plus 3 into 6 cube. Now this is 500 upon 500 plus 648, which is 500 upon 1148. And if we simplify this, it comes out to be 125 upon 287. So basically this problem, it is a mix of binomial probability, because we are replacing the ball every time, and Bayes theorem. Now here the question is, a letter is known to have come from either Krishnagiri or Dharmapuri. On the postmark, only 2 consecutive letters RI are visible. Then the chance that it came from Krishnagiri is, we have 2 events, either it can come from this Krishnagiri or it can come from Dharmapuri. Let us say this event K is, it has come from Krishnagiri, and event B, that it has come from Dharmapuri. Now getting a letter from either of these 2 places is equally likely. So this probability, it is 1 by 2, and this probability is also 1 by 2. Now let us take this event A, that the 2 consecutive letters visible are RI. So if we find this probability, that probability A by K and LB. Now if we look at Krishnagiri, the possible 2 combinations are, so we have to choose any 2 consecutive, and we know that in a row, number of consecutive selections is given by n minus r plus 1. Now in this case, n is 5 and 5, 10, 11. 11 minus 2 plus 1. There will be 10 ways. And our favorite case is when Ri is visible. Now we get Ri here and we also get Ri here. So this probability will be simply 2 by 10. Then the same way, if we look at RI in Dharmapuri. Now here we have 5 and 5, 10. So here it will be 10 minus 2 plus 1, which is 9. And from these 9, the favorable condition is only 1. So it will be this 1 by 9. Now it's a Bayes theorem question that we know that if the letters RI are visible, then it has come from Krishnapuri. So we'll take this case in the numerator. So it will be this 1 by 2 into 2 by 10 upon 1 by 2 into 2 by 10 plus 1 by 2 into 1 by 9. Now this 1 by 2 will cancel. Now this is 1 by 5 and this is 1 by 5 plus 1 by 9 and will be this 9 by 14, and that's your option C. Now the question is, a die A has 2 white and 4 red faces, where die B has 4 white and 2 red faces. A coin is flipped once. If it shows heads, then game continues by throwing die A, and if it shows tail, then die B is used. If the probability that die A is used is 32 by 30, when it is given that red turns up every time in first n throws, find the value of n. Now first we toss a coin. Either we'll get a head or a tail. The probability of getting heads is 1 by 2 and probability of getting tail is 1 by 2. Now if it is a head, then we throw this die A. Now if we throw die A, then red turns up every time in first n throws. So probability of getting red, it is 4 by 6 and there will be 2 by 3. So this probability will be 2 by 3 to the power n. And if it is tail, then we roll this die B which has 4 white and 2 red. Now getting all n reds is 1 by 3 to the power n. Now this is for die A and this is for die B. Now it is given that red turns up every time, then the probability that it is die A, it is a Bayes theorem question. So if it is Bayes theorem question, if it is red, then this is die A. So this case will come in the numerator. So it will be this 1 by 2 and 2 by 3 to the power n divided by this total case, which is 1 by 2, 2 upon 3 to the power n plus 1 by 2 into 1 upon 3 to the power m. It is 32 by 33. Now this 1 by 2 will cancel. Now we can write this as 2 to the power n upon 2 to the power n plus 1. So which is 2 to the power 5 upon 2 to the power 5 plus 1. So value of n is nothing but 5. So in this case, the value of n is 5, and that is the answer to this question. Now here the question is, a purse contains 2 coins, of which one is a 2-headed coin and the other one is a fair coin. A person selects one of the coins at random and tosses. If he gets heads, he tosses the other coin. Otherwise, he tosses the same coin. It is given that he got head in the second toss. Find the probability that this first selection is a fair coin and getting heads is which of the following. Now, a purse contains 2 coins. One of them is fair coin and the other one is 2-headed coin. Now, probability of choosing a fair coin, it is 1 by 2, and probability of choosing a 2-headed coin is 1 by 2. Now, if a fair coin is tossed, we get 2 outcomes. Either it will be this heads or tails. We'll get heads with the probability 1 by 2 and tails with the probability 1 by 2. Now, if it is heads, he tosses the other coin. So, in this case, if the first coin is fair, he's going to toss this 2-headed coin. And in this case, probability of getting a heads, it is simply 1. Now, if it is tails, he tosses the same coin. So, if it is tails, then again it could be either heads or tails, which again is 1 by 2 and 1 by 2. Now, if he has chosen this 2-headed coin, he's going to toss. He'll get this heads. And once he gets heads, he has to toss now a fair coin, which can result in either heads or tails. So, it will be this 1 by 2 and 1 by 2. Now it says, it is given that he got heads in the second toss. Now we need to find this probability that first selection is a fair coin and getting heads. So that means first coin, it should be fair and we should get a head. So this case, it should be in the numerator and all other cases will be in the denominator. So this required probability will be this 1 by 2 into 1 by 2 into 1 upon, now this is 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2 into 1 by 2 and plus this case which is 1 by 2 into 1 into 1 by 2. So 1 by 2 into 1 into 1 by 2. Now we divide everything with 1 by 4, we get 1, and this is 1 plus 1 by 2 plus 1. So this probability will be simply 2 by 5, and that's your option C. Now here the question is, a box contains n coins out of which m are fair and rest are biased. The probability of getting a heads when a fair coin is tossed is 1 by 2 and it is 1 by 3 when it is a biased coin. A coin is drawn from the box at random and is tossed twice. First time it shows heads and the second time it shows tails. What is the probability that coin drawn is fair? Now in this box we have m fair coins and then n minus m biased coins. Now once we choose a coin, it can be either a fair coin or it can be a biased coin. Now probability of choosing a fair coin, it is m by n, and probability of choosing a biased coin, it is n minus m by n. Now if we toss a fair coin, it can result in either heads or tails, and if we toss it again, we'll get again heads tails. Here also it will be this heads and tail, and for this biased coin also we'll have these results as heads tails and heads and tails. This is tails. Now for this fair coin, probability of getting heads or tails, it is simply 1 by 2, so it will be this 1 by 2 throughout. And for this biased coin, probability of getting a heads, it is 2 by 3, and getting a tails is 1 by 3. Now again this is 2 by 3, 1 by 3, and this is again 2 by 3 and 1 by 3. Now it says the coin is drawn, it first shows heads and then it shows tail. First head then tail, so it is this case in case of a fair coin, and in case of a biased coin it is this case. Now it says what is the probability that coin drawn is fair? So clearly it is a Bayes theorem question. So if it results in this combination head tail, then we have to find the probability that it is a fair coin. So we'll take this fair coin case in the numerator, which is m by n into 1 by 2 into 1 by 2 upon total cases, which is m by n into 1 by 2 into 1 by 2 plus n minus m by n into, now this is 2 by 3 into 1 by 3. Now we can cancel this n with n, so it will be this m by 4, and here we'll get this as m by 4 plus 2 n minus m by 9. Now we simplify this, we'll get this as 9m upon, now this is 9m minus 8m, so there will be m plus 8n, and this is the required probability that we are looking for. Now here the question is, in a test, an examinee either guesses or copies or knows the answer to a multiple choice question with 4 choices. The probability that he makes a guess is 1 by 3. So making a guess, it is 1 by 3. He copies the answer, it is 1 by 6. Now knowing is 1 minus sum of these two, as these 3 are mutually exclusive and exhaustive. So it will be 1 minus 1 by 3 plus 1 by 6, and that should be 1 by 2. Now probability his answer is correct given that he guesses it. Now there are 4 options out of which 1 is correct. So this probability when A by G, it is 1 by 4. Probability answer is correct given that he copies it, it is given as 1 by 8. And probability that his answer is correct when he knows the answer, it has to be 1. Now we need to find the probability that he knew the answer given that he answered it correctly. So that means it's a Bayes theorem question, and we need to find he knows the answer given that his answer is correct. So we'll take this case in the numerator, so it will be this 1 by 2 upon, now this is 1 by 3 into 1 by 4, 1 by 12, 1 by 6 into 1 by 8, 48, and plus 1 by 2. Now this is 1 by 2. This is 4 plus 1 plus 24 by 48. So it will be this 24 by 29, and that is the answer to this question. Now here the question is, a box contains 12 identical balls, of which 12 are white and 12 are black. The balls are drawn at random from the box one at a time with replacement. The probability that a white ball is drawn for the 4th time on the 7th draw is. Now we have 6 draws, and this 7th draw, it must be a white ball. Now in the first 6, it has to be 3 white and 3 black. Now which 3 white? It'll be this 6C3. Then probability of drawing a white ball, it is 1 by 2, and probability of drawing a black ball is also 1 by 2. So it will be this 1 by 2 to the power 6, and then probability of getting this 7th ball is white, it will be this 1 by 2. Now this is 20 upon 2 to the power 7, which is 5 by 32, and that's your option C. Now question number 23, it's a Bayes theorem question. It says a bag contains some candies, 2/5 of them are made of white chocolate and 3/5 are made from dark chocolate. So we have two kind of chocolates. So some of them they are white and some of them they are dark. So the probability that we get a white chocolate is 2 by 5, and the probability of getting a dark chocolate is simply 3 by 5. Now out of white chocolates, 1/3 are wrapped in red papers. So these chocolates, they're wrapped in either red papers or blue paper. So the probability that white chocolate, they're wrapped in red paper is 1 by 3, and it is wrapped in blue paper will be 2 by 3. In the same way for dark chocolate, the probability that it is wrapped in red paper is 2 by 3, and probability that it is wrapped in blue paper is 1 by 3. Now it says if a randomly selected candy from the bag is found to be wrapped in red paper, then what is the probability that it is made up of dark chocolate? So it is a Bayes theorem question. So we need to find the probability that it is made up of dark chocolate when it is wrapped in red. So that means we need to find this probability that it is dark when it is wrapped in red. So we'll put this case when it is a dark chocolate and with red paper in the numerator. So it will be simply 3 by 5 into 2 by 3, and in the denominator we'll put the probability of getting a red paper. So we'll get a red paper when it is white and red or when it is dark and red. So here will be 2 by 5 into 1 by 3 plus 3 by 5 into 2 by 3. So this probability of getting a dark when it's a red paper is, so this is 6 by 15, and here it is 8 by 15. So it is simply 3 by 4, and that's your option number B. Now we'll come to the section B, and the first question is, out of 14 students taking test, 5 are well prepared, 6 are adequately prepared, and 3 are poorly prepared. So we have 3 set of students. So suppose event W, it has set of well prepared students, A set of adequately prepared, and then P set of poorly prepared students. The probability of choosing a student from the set of well prepared will be simply 5 by 14, adequately prepared will be 6 by 14, and poorly prepared will be 3 by 14. Now there are 10 questions on the test paper. A well prepared student can answer 9 questions correctly. An adequately prepared student can answer 6, and a poorly prepared student can answer only 3 questions correctly. Now for each probability below, write down your final answer as a rational number in lowest form. If a random student is asked 2 distinct random chosen questions from the test, what is the probability that student will answer both questions correctly? Let us say event C is student answers the question correctly. Now if the student is well prepared, then the answers will be correct with the probability 9C2 upon 10C2. Now if the student is adequately prepared, then the probability of getting 2 questions correct is 6C2 upon 10C2, and if it is poorly prepared, then the probability of getting 2 correct is 3C2 upon 10C2. Now we need to find the probability that a student will answer both questions correctly. So it is conditional probability question. The probability that student will answer a question correctly is when we multiply each of these corresponding probabilities. So it will be 5 by 14 into 9C2 upon 10C2 plus 6 by 14 into 6C2 upon 10C2 plus 3 by 14 into 3C2 upon 10C2, which is 31 by 70. Now part B is, suppose the student was chosen at random and asked 2 selected questions from the exam and did answer both questions correctly. Find the probability that chosen student was well prepared. Now this is Bayes theorem question. So if the student is well prepared, then we'll take this case in the numerator. If the questions are answered correctly, then the student is well prepared. It will be 5 by 14 into 9C2 upon 10C2 upon 31 by 70. So it will be 20 by 31. Now here the question is, a mother and her 2 daughters participate in a game show. At first, the mother tosses a fair coin. If the result is heads, then all 3 win individual prizes and the game ends. And if the result is tails, then each daughter separately throws a fair die and wins a prize if the result of a die is 5 or 6. Now first, mother tosses a coin, and if she gets heads, then all of them, they win. And if it is tails, then both the daughters, they roll a die, and if they get 5 or 6, they win, else they lose. So for both of them, we'll have these conditions. Now getting a heads, it is 1 by 2. Getting a tail, probability is 1 by 2. Daughter 1 winning, her probability is 1 by 3. Losing is 2 by 3. And the same way for second daughter, it will be 1 by 3 winning and 2 by 3 losing. Now the first question is, suppose the first daughter did not win a prize, then what is the probability that second daughter also did not win a prize? So we need to find this conditional probability that second daughter did not win a prize when first one did not win. So we'll have this probability as probability of D1 intersection D2 upon probability of D1. Now both of them, they'll not get a prize only when if it is tails. So if it is tails, we'll get 1 by 2, and then both of them, they independently do not get 5 or 6. So it will be 2 by 3 into 2 by 3. Now divided by probability of first daughter not getting a prize. Again, it will be this 1 by 2, and she won't get a prize if the probability is 2 by 3. So we'll cancel. So answer to this first part is simply 2 by 3. So if first daughter did not win a prize, the probability that second daughter will also not win a prize is 2 by 3. Now in the part B, it says, suppose the first daughter won a prize, what is the probability that second daughter also won a prize? We need to find this probability that second daughter wins the prize if first one wins the prize. So it will be this probability W1 intersection W2 upon probability of W1. Now probability of W1 is either when we get heads, so it will be this 1 by 2, or when it is this 1 by 2 and she gets 5 or 6, so it will be this 1 by 3. And the case when both of them wins, it could be this first case when it is 1 by 2, or the second case when they get tails, both of them they won a prize, so it will be 1 by 3 into 1 by 3. Now this 1 by 2 will cancel, so we'll get this as 1 plus 1 by 9, and there will be 10 by 9 divided by, now this is 1 plus 1 by 3, and there will be 4 by 3. Now this is 3, it will be simply 5 by 6. So the probability that second daughter also won a prize, provided first daughter wins it, is 5 by 6. Now question number 26 is, in a factory there are 3 machines X, Y and Z, and they produce 1000, 2000 and 3000 bolts every day. Now the probability that bolt is manufactured by X is 1000 by 6000, so it will be 1 by 6, Y is 2 by 6 and Z is 3 by 6. Now defective percentage of each of these machines are 1, 1.5 and 2. So probability of getting defective from X, it is 1 by 100. Defective from Y, it is 1.5 by 100. And defective from Z, it is 2 by 100. Now it says a bolt is found to be defective. What is the probability that this bolt is produced in machine X? So it's a Bayes theorem question. So if it is defective, it came from machine X. So we'll take this case in the numerator. So it will be 1 by 6 into 1 by 100 upon 1 by 6 into 1 by 100 plus 2 by 6 into 1.5 by 100 plus 3 by 6 into 2 by 100. So this 100 into 6 will cancel. So we'll write this probability as 1 upon, and this is 1 plus 3 plus 6. So it will be simply 1 by 10, and which is none of these. Option number D. Now here the question is, in a purse there are 10 coins, all 5 paisa except one, which is a rupee. In another purse there are 10 coins, all 5 paise. 9 coins are taken from the former purse and put into the latter, and 9 coins are taken out from the latter and put into the former. The chance that the rupee is still in the first purse is, now we need to find the chance that the rupee is still in the first purse. And the first purse, say P1, we have 9 5 paise coins and we have 1 rupee coin. And in the second purse, we have 10 5 paise coins. Now 9 coins are taken and they are transferred to this second purse. Now we have two cases. Case 1, all the 9 are 5 paise coins, or there are 8 5 paise coins and 1 rupee coin. Now in the first case, since 1 rupee is already there in this purse 1, so we have to put any 9 5 paise coins. But in the second case, we have to put 8 5 paise coins along with 1 rupee coin. So now we start writing this probability. Now this first case is when we have transferred 9 5 paise coins. So there will be 9C9 upon 10C9 into, now from this we have transferred 9 out of 19 5 paise coins. So there will be 19C9 upon 19C9. Now this plus second case when we have 8 5 paise coins, so it will be 9C8 into 1C1 upon 10C9 into, now from this we have to select 8 5 paise coins and 1 rupee coin. So there will be 1C1 and then we have 18C8 out of 19C9. Now this is 1 by 10. Now 9C8 is 9, 10C9 is 10, and this is factorial 18, factorial 8, factorial 10, and here it is factorial 19, factorial 10, factorial 9. Now 10 will cancel, here it will be this 9 and here it will be this 19. So we'll get this as 119, and this is 19 plus 81. So it will be this 100 by 190, and that is 10 by 19, and that's your option B. Now the next one is, every evening Mr. X either reads a book or watches TV. So this Mr. X, he either reads a book or he watches TV. Now probability that he watches TV is 4 by 5. So this is 4 by 5. Then probability of reading a book is 1 by 5. If he watches TV, then there is a probability of 3 by 4 that he falls asleep. So while watching TV, he falls asleep with the probability 3 by 4, and he does not sleep. This probability is 1 by 4. And if he reads a book, the probability that he falls asleep is 1 by 4. So while reading a book,
He'll fall asleep with the probability 1 by 4. And he doesn't sleep with the probability 3 by 4. Now, on one evening, Mr. X is found to be asleep. Find the probability that he watched TV. So, this again is a case of Bayes' theorem. So, he's found to be asleep. We need to find the probability that he was watching TV. So, this probability that he was watching TV, if it is found that he was asleep, this is going to be, now this case in the numerator, which is 4 by 5 into 3 by 4 upon, now these two cases, which is 1 by 5 into 1 by 4 plus 4 by 5 into 3 by 4. Now this is simply 12 by 13, and that's your option B. And this third question in Bayes' theorem is, a pack of 52 playing cards is counted with face downwards. If it is found that one card is missing, then one card is drawn and found to be red. Find the probability that missing card is red. So this missing card, it can be either red or black. The probability of it to be red, it is 1 by 2, and black is also 1 by 2. Now if the card lost is red, then probability of getting a red card, it will be 25 by 51. And if the card lost is black, then probability of getting a red card will be simply 26 by 51. Now it is known that the drawn card is red. Find the probability that missing card is red. So we have to find this case. So if drawn card is red, then find the probability that missing card is also red. Now we'll take this case in the numerator. So it will be this 1 by 2 into 25 upon 51 divided by this total case, which is 1 by 2, 25 by 51 plus 1 by 2 into 26 by 51. Now 1 by 2 will cancel, 51 will also cancel. So this probability will be simply 25 by 51, and that's your option A. Now the question is, a box contains 3 coins, 2 of them are fair and 1 two-headed. A coin is selected at random and is tossed. If the head appears, the coin is tossed again. And if tail appears, then another coin is selected from the remaining coins and tossed. Find the probability that head appears at least twice. Now, first we are going to toss a coin. So this coin, it can be either a fair coin or it can be a two-headed coin. Now, if we toss a fair coin, it may result in either heads or tails. So it may come either heads or tails. If head appears, the coin is tossed again. So if it is head, then the coin is tossed again, and again we can have either heads or tails. And if it is tails, then another coin is selected from the remaining coins. Now once it is tails, then again we can have either a fair coin or a two-headed coin. Now if it is fair, we'll have two cases, heads or tails, and if it is two-headed coin, it'll be only heads. Now again for this two-headed coin, it'll be this heads, and this same coin is tossed again. So again we'll get this head. Now we'll start writing these probabilities. Now there are two fair coins. The probability of choosing a fair coin is 2 by 3, and here two-headed coin probability is 1 by 3. Now getting a heads, it is 1 by 2. Getting a tails, 1 by 2. Now here also it is 1 by 2 and 1 by 2. Now here getting a fair coin, now we are left with one fair and one two-headed coin. So it will be this 1 by 2 into 1 by 2. And here from a fair coin, getting a heads and tails is 1 by 2. From a two-headed coin, getting a heads is simply 1. So this is 1 and 1. Now first is find the probability that head appears twice. Now head, it appears twice in this case and in this case. So there are only two cases possible. So this probability is this 2 by 3 into 1 by 2 into 1 by 2 and plus 1 by 3. Now this third one is find the probability that tail appears twice. Now tail appears twice only in this case. So
this third one, the probability that tail appears twice will be this 2 by 3 into 1 by 2 into 1 by 2 into 1 by 2, which is simply 1 by 12. So this probability will be 1 by 12, and that is the answer to this question. Now here the question is, with respect to a particular question on a multiple choice test having 4 alternatives with only one correct, a student knows the answer and therefore can eliminate 3 of the 4 choices from consideration with probability 2 by 3. So the probability that student knows the answer, it is 2 by 3. Now he can eliminate 2 of the 4 choices from consideration with probability 1 by 6. So this second case, when he can eliminate 2 choices, this probability, it is 1 by 6. One choice with probability of 1 by 9. So eliminating one choice, it is 1 by 9, and can eliminate none with the probability 1 by 18. So if it is none, then it is 1 by 18. Now if we add them all up, their sum is 1. So all these cases, they are mutually exclusive and exhaustive. Now probability of getting the answer correct, if he knows the answer, it is simply 1. Probability of getting the answer correct, if he can eliminate 2 choices, it will be simply 1 from the remaining 2 choices. Probability of getting the answer correct, if he can eliminate 1 choice, it will be simply 1 out of 3 choices. And if he cannot eliminate any of the choices, then this probability will be simply 1 out of 4, which is 1 by 4. Now it says, if the answer given by the student was found correct, then the probability that he knew the answer is A by B, where A and B are relatively prime. Find the value of A plus B. Now it's a Bayes theorem question. So if his answer is correct, then he probably knew the answer. This probability will go in the numerator, and all the probabilities, they'll go in the denominator. So this probability A upon B will be equal to this 2 by 3 into 1 upon all these probabilities, which are 2 by 3 into 1 plus 1 by 6 into 1 by 2 plus 1 by 9 into 1 by 3 plus 1 by 18 into 1 by 4. So it will be this 2 by 3 upon 2 by 3 plus 1 by 12 plus 1 by 27 plus 1 by 72, 2 by 3 upon 173 upon 216. If we simplify this, we'll get this as 144 upon 173. Now we need to find the value of A plus B. So the value of A plus B will be 144 plus 173. So which is 7, 1 and 3. So answer to this question is 317. The question is, let N1 and N2 be number of red and black balls respectively in box 1. And let N3 and N4 be number of red and black balls in box 2. So we have 2 boxes, box 1 and box 2. Now in box 1 we have N1 red and N2 black balls, and here we have N3 red and N4 black balls. Now one of the 2 boxes was selected random and a ball was drawn randomly out of this. The ball was found to be red. The probability that this red ball was drawn from box 2 is 1 by 3. Then which of the possible values of N1, N2, N3, N4 is or are? Now basically it's a problem of Bayes theorem. So if ball is found to be red, then the probability that it has come from this second box will be given by, now probability of choosing this second box, it is 1 by 2, and then probability of choosing a red ball from this second box is N3 upon N3 plus N4 divided by total number of ways. Now total number is, if it is first box, we can choose it in 1 by 2 ways, and then getting a red ball is N1 upon N1 plus N2 plus 1 by 2 into N3 upon N3 plus N4, and this probability is 1 by 3. Now 1 by 2 will cancel. Now we can simplify this as n3 into n1 plus n2 upon n1 into n3 plus n4 plus n3 into n1 plus n2, and this is equal to 1 by 3. Now we can write this as 3 n1 n3 plus 3 n2 n3, and it will be equal to n1 n3 plus n1 n4 plus n1 n3 plus n2 n3. Now n1 n3 twice will cancel here. Now this n2 n3 will be this 2, so we can write 2 times n2 n3, it must be equal to n1 into n4 minus n3. Now we have to check all the options. Now 2 into n2 n3, so here will be this 15 into 2 is 30, and n1 is 3, and n4 minus n3 will be this 10, so it will be this 30. That means this option A, it is correct. Option B is 6 and 10, 60, 60 into 2, 120, n1 is 3, and n4 minus n3 is 40, so it will be this 120. Option B is also correct. Now this is 2 into 6 into 5, so it will be this 60, and here it is 8 into 15, 15 into 8 is 120, so that means option C is incorrect, and here it is 12 into 5 into 2, 120, and it will be equal to n1, which is 6 into 15, 15 into 6 is 90, so this is also incorrect. So the only correct options are A and B. Then the second part, it says a ball is drawn at random from box 1 and it is transferred to box 2. If the probability of drawing a red ball from box 1 after this transfer is 1 by 3, then the correct options with possible values of n1 and n2 are. Now from the box 1, we have transferred one ball. Now this ball, it could be red or it could be black. Now it is red with the probability n1 upon n1 plus n2. It is black with the probability n2 upon n1 plus n2. Now after this transfer, we have drawn a ball from this first one. Now this first one has n minus 1 red and n2 black. So probability of drawing a red ball is n1 minus 1 upon n1 plus n2 minus 1, and in this case it will be n1 upon n1 plus n2 minus 1. So probability of drawing a red ball after this transfer will be n1 into n1 minus 1 plus n1 into n2 upon n1 plus n2 into n1 plus n2 minus 1, and this probability is equal to 1 by 3. Now here if we take n1 common, we can write this as n1 plus n2 minus 1 upon n1 plus n2 upon n1 plus n2 minus 1, and this is 1 by 3. Now here it will cancel, so this probability will be n1 upon n1 plus n2 will be equal to 1 by 3, or 2n1 must be equal to n2. Now option A, it is not true. Option B is also not true. Correct options are C and D. And that is the answer to this question. Now here the question is, let H1, H2 and Hn be mutually exclusive and exhaustive events such that probability of Hi is greater than 0, and let E be any other event with probability of E lying between 0 and 1. Now statement 1 is probability of Hi upon E is greater than probability of E upon Hi into PH1 because summation PHI equals 1. Now, since these events are mutually exclusive and exhaustive, then clearly summation phi will be 1, where I varies from 1 to n. So that means the statement 2, it is correct. Now, if we look at probability of hi upon e, we can write this as probability of hi intersection e upon probability of e. Now what we can do is we can multiply and divide it with phi. We are going to write this as phi intersection e upon phi into phi upon pe. Now this is nothing but this is pe upon hi. So there will be p e upon hi into phi divided by pe. Now since pe lies between 0 and 1, so it will be greater than p e upon hi into phi. So the statement 1, it appears correct, but then there is this one case if phi intersection e is 0, then in that case left hand side and right hand side, they both become equal to 0. In that case the statement 1 is not correct. So the statement 1 is not always correct. So in some books you'll find this answer as both the statements are correct and statement 2 doesn't explain statement 1. And in some books you'll find it, they'll say statement 1 is wrong and statement 2 is correct. However, one of the iconic teachers, Professor K.D. Joshi from IIT Bombay, he maintains that both the statements are correct and statement 2 doesn't explain statement 1. Now here the question is, X and Y are 2 weak students in mathematics and their chance of solving a problem correctly are 1 by 8 and 1 by 12. So probability that X solves the problem correctly is 1 by 8 and Y solves the problem correctly is 1 by 12. Now it says they are given a question and they obtain the same answer if the probability of common mistake is 1 upon 1,001, then the probability that answer was correct is A upon B, where A and B are co-prime. Then find the value of mod A minus B. Now let us consider two events. Event E1, when both of them they solve correctly, and then this event E2, when both of them they solve incorrectly. Now this probability that both of them they'll solve the question correctly, it is given by this probability of X into probability of Y, since they are solving the problem independently. So this probability will be 1 by 8 into 1 by 12. So it will be 1 by 96. And the probability that they'll solve the problem incorrectly, it will be this Px naught into Py naught. Now Px naught is 7 by 8 and it is 11 by 12. So there will be 77 by 96. Now let A be the event that their answers match. Now if both of them they have solved the question correctly, then the probability of their answer matching will be 1. But if they have solved the problem incorrectly, then probability of their answer matching, it is given by 1 upon 1001. Now we need to find the probability that their answer was correct, given that they obtained the same answer. So basically it's a problem of Bayes theorem. So we have to find probability that their answer was correct, given that they have a common answer. So we'll take this case in the numerator. So it will be this 1 into 1 by 96 upon 1 into 1 by 96 plus 77 by 96 into 1 upon 1001. Now this 96 will cancel. Now 77 divided by 1001 is 13. So this probability will be 13 by 14. And that's your A upon B. Now modulus value of A minus B is simply 1. And that is the answer to this question. Now here the question is, a box B1 contains 1 white, 3 red and 2 black balls. Another box B2, it contains 2 white, 3 red and 4 black balls. And another box B3, it contains 3 white, 4 red and 5 black balls. Now if one ball is drawn from each of the boxes B1, B2 and B3, find the probability that all drawn balls are of same color. Now all the 3 balls, they have same color if all 3 of them are W. So it will be W, 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 or red, red and red, or black, black and black. Now this probability, now white from this first box, it is 1 by 6. White from second, it is 2 by 9. And white from third, it is 3 by 12. Now if it is all red, then it will be this 3 into 4 divided by 6 into 9 into 12 and plus 2 into 4 into 5 upon 6 into 9 into 12. Now this is 6 plus 36 plus 40 divided by 108 into 6. Now this is 82 upon 648, and that's your option A. Now the second question is, 2 balls are drawn without replacement from a randomly selected box, and one of the ball is white and the other ball is red. The probability that these 2 balls are drawn from box B2. Now this is Bayes theorem question. Now these 2 balls, they may be from box B1 or B2 or B3. Now probability of choosing any one box, it is 1 by 3, 1 by 3 and 1 by 3. Now if we choose B1, then the probability of getting 1 white and 1 red will be 1C1 into 3C1 upon 6C2. Now for second it will be 2C1 into 3C1 upon 9C2, and here will be 3C1 into 4C1 upon 12C2. Now this is 3 by 15 and 3 by 15 is 1 by 5, and this is 6 by 36, which is 1 by 6, and here it is 12, and this is 6 into 11, which is 2 by 11. Now if this event, say A, it has already occurred, we have to find the probability that the ball is drawn from the box 2. So we have to find P B2 by A. So we'll take this case in the numerator. So it will be this 1 by 3 into 1 by 6 upon all the cases. So this is 1 by 3 into 1 by 5 plus 1 by 3 into 1 by 6 plus 1 by 3 into 2 by 11. Now this 3 will get cancelled. Now this is 1 by 6, and here it is 66 plus 55 plus 60 upon 55 into 6. Now this 6 will cancel. So this value will be 55 upon 126 plus 55, which is 181. And that's your option D. Now here the question is, 3 boys and 2 girls stand in a queue. The probability that number of boys ahead of every girl is at least 1 more than number of girls ahead of her. Now it could be boy, 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 and then the two girls, or it could be boy, boy, girl, boy and girl, or it could be boy, boy, girl, girl and boy, or it will be this boy, girl, boy, girl and boy, or it could be boy, girl, boy, boy and girl. So these are the 5 possibilities. So it should start with boy, because before any girl, number of girls is 0, so it should have at least one boy. All these permutations, they'll start with a boy, and then we have to follow the given condition. Now in each arrangement, we have 3 places for boys and 2 places for girls, and in which they can be arranged in factorial 3 into factorial 2 ways. So total number of ways of arranging them with the given condition will be simply 5 into factorial 3 into factorial 2 divided by total number of ways. Now total number of ways of arranging these 5 people will be simply factorial 5. So this probability will be nothing but 1 by 2, and that's your option A.
Now this part B, it says, in a combat, A targets B and both B and C, they target A. The probability of A, B and C hitting their targets are 2 by 3, 1 by 2 and 1 by 3 respectively. Now they shoot simultaneously and A is hit. Find the probability that B hits its target while C does not. Now in this combat, A targets B, whereas B and C, they both target A. Now probability of A hitting their target, it is 2 by 3. For B, this probability is 1 by 2, and for C, this probability is simply 1 by 3. Now it says A is hit. Now A is going to be hit if both B and C, they hit the target, or B hits and C misses, or B misses and C hits the target. Now we have to find this probability that B hits his target whereas C does not. That means B hits his target whereas C does not. So basically this is the condition for Bayes theorem. So we have to find this probability that B hits and C does not, provided A is hit. Now for this, we'll take this case in the numerator. So it will be this probability of B intersection C naught divided by this complete probability, which is probability of B intersection C plus probability of B intersection C naught plus probability of B naught intersection C. Clearly, these events are independent. So we can write this as probability of B, and probability of B is 1 by 2 into probability of C naught, and probability of C naught is 2 by 3. Here it will be B and C, so it will be 1 by 3 into 1 by 2 plus B, it is 1 by 2, and C naught is 2 by 3, and plus B naught is 1 by 2, and C is simply 1 by 3. Now it will be this 2 divided by, now this is 4, so this required probability is 1 by 2. So if A is hit, then the probability that B hits and C misses, it is simply 1 divided by 2. Now here the question is, a computer producing factory has only 2 plants, T1 and T2. Plant T1 produces 20% and plant T2 produces 80% of the total computer produced. So we have 2 plants, T1 and T2. Now plant T1 handles 20% of the production. So this probability of choosing a product from T1, it is 20 by 100, and from T2, this probability will be 80 by 100. If 7% of the computers produced in the factory turns out to be defective, so overall defective will be 7 by 100. It is known that probability computer turns out defective given that product is from plant T1, it is 10 times probability. Computer turns out it is defective, it is produced in plant T2, and suppose this is X. Now first one is probability it is defective. If it has come from plant T1, it will be X,
and probability that it is defective if it has come from plant T2, it will be simply x by 10. So from this given information, first we'll find the value of x. Now probability of getting defective will be either we get defective from T1 or we get defective from T2. So it will be this 20x by 100 plus 80x by 1000 and will be equal to 7 by 100. Now this will cancel. So we'll get this as 28x equals 7. Value of x is 1 by 4. So probability of getting a defective from T1, it is 1 by 4, and probability of getting defective from T2, it is 1 by 40. Now it says a computer produced in the factory is randomly selected and it does not turn out to be defective. Find the probability that it is produced in plant T2. Now for this, first we'll calculate this probability, which is probability it is not defective if it has come from T1. Now we know that probability of A upon B plus probability of A naught upon B, it is equal to 1. So probability of D naught upon T1 will be simply 3 by 4 and probability of D naught upon T2 will be 39 by 40. So now again we have two plants, T1 and T2. Getting it from T1, it is 20 by 100, T2 is 80 by 100. Not defective from T1, it is 3 by 4. Not defective from T2, it is 39 by 40. Now, if it is non-defective, find the probability that it has come from T2. So we have to find this conditional probability that if it is not defective, it has come from T2. So we'll take this case in the numerator. So it will be this 80 by 100 into 39 by 40 divided by this 20 by 100 into 3 by 4 plus 80 by 100 into 39 by 40. Now this 0 0 will cancel. We'll cancel this 400. So it will be this 8 into 39 upon 60 plus 8 into 39, which is 312 upon 372, which is 26 by 31. So it is 26 by 31, or if we multiply it with 3, we'll get this as 78 upon 93, and that's your option C. Now here the question is, a signal which can be green or red with probability 4 by 5 and 1 by 5 is received by station A and then transmitted to station B. The probability that each station receiving the signal correctly is 3 by 4. If the signal received at station B was green, find the probability that original signal was also green. Now this signal, it can be either green or red. Now it is green with the probability 4 by 5 and it is red with the probability 1 by 5. Now this green signal, it can be received at station A as either green or red. In the same way, this red signal also can be received as either red or green. Now it will be received green if it received the signal correctly. So it will be this 3 by 4 and here will be this 1 by 4 and red as red again is 3 by 4 and red as green as 1 by 4. Now it says at station B the signal received is green. So at B it will be green if it is received correctly. So it will be this 3 by 4. Now red will be received as green if it is 1 by 4. Now red as green this is 1 by 4 and green as green, it will be simply 3 by 4. That is given that the signal received at station B is green. We need to find this probability that original signal was green. So we have to take this case in the numerator and all of the cases in the denominator, and that's how we'll get this probability. So this probability will be 4 by 5 into 3 by 4 into 3 by 4 plus 4 by 5 into 1 by 4 into 1 by 4 divided by 4 by 5 into 3 by 4 into 3 by 4 plus 4 by 5, 1 by 4, 1 by 4 plus 1 by 5, 3 by 4, 1 by 4 plus 1 by 5, 1 by 4 into 3 by 4. Now all these denominators, they'll get cancelled. So this probability will be 36 plus 4 divided by 36 plus 4 plus 3 plus 3. Now this is 40 divided by 46, which is 20 by 23, and that's your option C.
Now here the question is, there are two lots of identical articles with different amount of standard and defective articles. There are n articles in the first lot and n of which are defective, and capital M articles in the second lot, of which small m are defective. If k articles are selected from the first lot and L from second, a new lot results. Find the probability that an article selected at random from the new lot is defective. Now the article which is selected from this new lot, it can either come from lot 1 or it can come from lot 2. Now the new lot, we are choosing k articles from lot 1 and L articles from lot 2. So probability of choosing an article from first lot is k upon k plus L, and the probability of choosing an article from second lot is L upon k plus L. Now we need to find the probability that it is defective if it has come from this first lot. Now in the first lot, small n are defective. So this probability will be simply n by capital N, and here if it is from second lot, the probability of it being defective will be small m by capital M. So the probability that selected or chosen article will be defective will be given by probability of first intersection and defective or probability of second intersection defective, and we can solve it using conditional probability. So it will be k upon k plus L into n by n plus L upon k plus L into small m by n. So it will be simply kn capital M plus L small n capital N upon k plus L into capital M capital N, and that is the answer to this question. Now in this question we are given that a box contains 5 radio tubes, out of which 2 are defective. The tubes are tested one after the other until the 2 defective tubes are discovered. Find the probability that the process stops on the second test. Now this process will stop on the second test if first one is defective and second one is also defective. Now this required probability that first tube is defective and second tube is defective will be given by, now for the first tube we have 2 defective out of 5, so this probability will be simply 2 by 5, and for the second one, since first tube it is already gone, we have 1 defective from the remaining 4, so this probability will be simply 1 by 10. Now in the second part it says find the probability that the process stopped on the third test. Now this process, it will stop in the third test if we have, suppose, defective and right and defective, or right
defective and defective, or we get all three right, then in that case, the remaining two, they'll be defective. Now, first one is defective. This probability is 2 by 5. Getting a right one, probability is 3 by 4. Again defective, so it'll be 1 by 3 plus, now right is 3 by 5. Defective is 2 by 4. Again defective, 1 by 3 plus, now right, it is 3 by 5, then 2 by 4, and then 1 by 3. Now this 3 will cancel, and this 2 will also cancel. So this required probability will be simply 3 by 10. Now this third problem is, if the process stopped on the third test, find the probability that the first tube is non-defective. Now the first tube is non-defective in this first case as well as in this second case. Now it becomes a problem of Bayes theorem. So provided the process stops on this third test, then first one is right. It is given by, now this right one will be in the numerator, which is simply 2 by 10 divided by probability that the process stops in the third test, which is 3 by 10. So this required probability will be simply 2 by 3, and that is the answer to this question. Now the question is, each of the n urns contain 4 white and 6 black balls. The n plus 1th urn contain 5 white and 5 black balls. Now out of these n plus 1 urns, an urn is chosen at random and 2 balls are drawn from it without replacement. Now both the balls turn out to be black. If the probability that the n plus 1th urn was chosen to draw the ball is 1 by 16, then the value of n by 2 is. Now either we can choose 2 balls from these n urns containing 4 white and 6 black, or we can choose this ball from this n plus 1th urn containing 5 white and 5 black ball. Now choosing this urn, probability is n upon n plus 1, and here the probability is 1 upon n plus 1. Now if we have chosen one of these urns, then probability of getting 2 black balls is 6c2 upon 10c2. Now in this case, this probability is 5c2 upon 10c2. Now it says the probability that n plus 1th urn was chosen is 1 by 16. So it is Bayes theorem condition. So we'll take this case in the numerator. So it will be 1 upon n plus 1 5c2 upon 10c2 by n upon n plus 1 6c2 upon 10c2 plus 1 upon n plus 1, and this is 5c2 into 10c2, and this value is 1 by 16. Now n plus 1 10c2 will cancel. We can add this as 10 upon, now 6c2 is 15. 15 n plus 10 and will be equal to 1 by 16. Now we can add this as 15n and will be 160 minus 10, 150. So value of n is 10. Now we need to find the value of n by 2. Value of n by 2 is 5. So in this case, value of n by 2 is 5, and that is the answer to this question.
Now here the question is, there are n urns each containing n plus 1 balls such that ith urn contains I white balls and n plus 1 minus I red balls. Let ui be the event of selecting ith urn and w denote the event of getting a white ball. Now if probability of ui is proportional to I, then find this limit n tends to infinite pw. Now it is given that pui is proportional to I, or probability of choosing ith urn, it is equal to k into I. Now choosing an urn, it is mutually exclusive and exhaustive. That means summation of all probabilities, it is equal to this summation k into I, and it is equal to 1. Now k is constant and summation I is n into n plus 1 by 2 equals 1. So value of k is 2 upon n into n plus 1. So probability of choosing ith urn will be equal to 2i upon n into n plus 1. Now first we'll find probability of getting a white ball. Now probability of getting a white ball, it's a conditional probability question where this probability is going to depend on the urn we are choosing. So this probability of getting a white ball will be equal to this summation where I varies from 1 to n PUI into PW upon UI. Now this is this summation. I varies from 1 to n. Now PUI is 2i upon n plus 1. Now from this ith urn, probability of choosing a white ball is I upon n plus 1. So this probability will be 2 upon n plus 1 square into summation I square. So this probability of getting a white ball, it is equal to 2n plus 1 whole square, and this is n plus 1 2n plus 1 whole divided by 6. Now here this 2 will cancel, n will cancel, and n plus 1 will also cancel. So this probability of getting a white ball, it is 2n plus 1, and this is 3 into n plus 1. Now we need to find this limit n tends to infinite. Now if we take this limit n tends to infinite PW, now highest power of n in this case is 1, and here also it is 1. So this limit is essentially the coefficient of highest power of n, which is 2 by 3. So the value of this limit is 2 by 3, and that's your option B. Now the next one is, if PUI is constant, then we need to find this Bayes theorem. If it is a white ball, it has come from the nth urn. Now first we'll find probability of getting a white ball in this second case. Now this second case will be equal to, again, this summation PUI and this PW upon UI, where I varies from 1 to n. Now this is this C, and here it is I upon n plus 1. So this is C upon n plus 1, and summation I is n into n plus 1 by 2. Now n plus 1 will cancel, so this probability is Cn by 2. Now we need to find this Bayes theorem condition that the ball has come from nth urn provided it is white. So we'll take this nth urn probability in the numerator. So it will be this C, and getting a white ball from nth urn is n upon n plus 1 divided by this whole probability of getting the white ball, which is Cn by 2. Now Cn will cancel, so this probability is 2 upon n plus 1, and that's your option A. Here the question is, a plane is landing. If the weather is favorable, then the pilot landing the plane can see the runway. In that case, probability of safe landing is P1. If there is a low cloud ceiling, then the pilot has to make a blind landing by instrument. The reliability of instrument needed for blind landing is capital P. If the blind landing instruments function normally, then the plane makes a safe landing with the same probability P1 as in the case of a visual landing. And if the blind landing instrument fails, in that case, pilot makes a safe landing with the probability P2, which is less than P1. Now compute the probability of safe landing if it is known that in K% of the cases, there is a low cloud ceiling. Also find the probability that the pilot used the blind landing instrument if the plane has landed safely. Now it is clearly conditional probability and Bayes theorem question. So first we have to cover for this nature. So either it can be favorable weather or there can be a low cloud ceiling. Now in K% of the cases, there is a low cloud ceiling. So this probability will be simply K by 100. And here in this case, this probability is 1 minus K by 100. Now if it is favorable weather, then the probability of safe landing is P1. So probability of safe landing when the weather is favorable, it is simply P1. Now in case of low cloud ceiling, pilot is going to rely on the instrument. Now this instrument
it can either work reliably or this instrument can fail. Now, probability of instrument working reliably, it is P, and if it fails, its probability is 1 minus P. Now, it is given that if instruments function normally, then the plane makes a safe landing with same probability P1. So, P safe in case of reliable landing, it is P1, and safe landing if instrument fails, this probability is P2. Now first we need to find the probability of safe landing. Now probability of safe landing will depend on these conditions. So this probability will be 1 minus K by 100 into P1 plus K by 100 into P into P1 and plus K by 100 into 1 minus P into P2. So here we can take K by 100 common. So we can write probability of safe landing as 1 minus K by 100 into P1 plus K by 100 P into P1 plus 1 minus P into P2. Now the second part is this Bayes theorem. Find the probability that pilot used the blind landing instrument if the plane landed safely. So we have to find this probability that this pilot, he has used instrument given that it has landed safely. We'll take this case when he has used the instrument in the numerator. So it will be this K by 100 P1 plus 1 minus P into P2 upon this total cases, which is 1 minus K by 100 into P1 plus K by 100 P1 plus 1 minus P into P2, and that is the answer to this question. Now here the question, we have 4 boxes. Box 1 contains 8 red, 3 blue, 5 green. Box 2 contains 24 red, 9 blue, 15 green. Box 3 contains 1 blue, 12 green, 3 yellow, and box 4 contains 10 green, 16 orange, and 6 white balls. Now it says a ball is chosen randomly from box 1 and call this ball B. Now if B is red, then ball is chosen from box 2. If B is blue, then it is chosen from box 3, and if it is green, then a ball is chosen randomly from box 4. So a ball is chosen from box 1. Now from this box 1, it can be either red or blue, or it can be green. Now probability of choosing a red ball, it is 8 by 16. Probability of choosing a blue ball, it is 3 by 16. And probability of choosing a green ball, it is 5 by 16. Now if it is red, we have to choose it from box 2. If it is blue, then from box 3. And if it is green, then we are choosing it from box 4. Now it says we have to find conditional probability of the event that one of the chosen ball is white given that at least one of the chosen ball is green. So this event, it must happen. That means at least one of the chosen ball is green. Now here if it is red, then from the second box we must get a green ball. Now from the second box, probability of getting a green ball is 15 by 48. In the same way, from this third box, we have to get a green ball. And from third, getting green is 12 by 16. And since in this third case, we already have a green ball, from this fourth box, we can have any one of green, orange, or white. Now, probability of choosing a green ball will be 10 by 32. Orange ball is 16 by 32 and white ball is 6 by 32. So these are all the cases in which at least one of the chosen ball is green. Now we have to find the conditional probability that one of the chosen ball is white. So we get white only in this case. So we'll take this case in the numerator and all other cases in the denominator, and that's how we'll get this conditional probability. So we have to find this conditional probability that one of the ball is white given that at least one ball is green. So it'll be this 5 by 16 into 6 by 32 upon, now this is 8 by 16 into 15 by 48 plus 3 by 16 into 12 by 16 plus 5 by 16 into this plus this, which is 1. So it'll be this value. Now we'll cancel this 16. Now this is 3 and 16, so it'll be 15 by 16. Now here this is 5, 16. So it'll be 40 by 16. This is 36 by 16, and 16 into 5 is 80 by 16. Now this 16 will also cancel. So it'll be this 15 upon 120 plus 36. So it'll be 156. And this is 5 by 52, and that's your option C.